Hello, good morning, good afternoon, or good evening. Welcome everybody to today's webinar on containerized deployments of embedded development tool chains. My name is Ricardo Camacho. I'm a Senior Technical Marketing Manager, and I'm joined by my good friend and colleague Miroslav Zielinski, Product Manager for our Safety Critical Solutions. We are very excited to share with you today. There's great information and content that we have on containerizations. But before we jump into the presentation, let's go over some housekeeping with Zoom. Now, first, everybody's microphone has been muted. However, if you have questions, please enter them into the Q&A dialog. You should see the Q&A button in your Zoom control panel. Also, if you run into any technical problems, like not being able to hear audio during the presentation, please use the chat channel. There you can connect with one of our team members who is ready to respond. Now let's run through a quick check to make sure everybody can hear me. Would someone click the raise hand button inside your chat channel if you can hear me? Okay. Perfect, thanks. Okay, looks like we are ready to start. I'm having a hard time going to the next slide. Thank you. On today's agenda, there will be a brief introduction to containers where basic terms and concepts will be covered. This is to make sure that we have a common framework for communicating and start from a level playing field. A key focus of our audience is embedded C, C++ development, so the presentation will be around using containers and the typical configurations in those types of environments or ecosystems. Also, very important is how to deploy these solutions. So a couple of workflows will be presented, IDE-based workflow and command line. And we actually have a really special treat. Miroslav is going to give us a quick live demonstration. So you're going to see containers in action. I'm actually very excited to see this. Next slide. All right, let's get started by asking Miroslav, our product manager and a friend of mine, to give us a brief summary of container technology and what it is. Miroslav, what are containers?
Thank you, Ricardo, for a great introduction. So let's talk about containers. Even though containers are used in the enterprise IT for many years, this is still a new technology for many teams developing embedded software. So I would like to start with a quick introduction to the subject, just to make sure everyone understands the basic concepts and terminology. So if you are a Docker expert, please bear with me for the next 10 minutes. So to start, with software containers, there is an analogy to the shipping industry, where instead of dedicated packaging and handling for all possible goods that are transported all over the globe, transport lines were optimized to operate with very well defined and fixed size of containers, which is, by the way, regulated by the ISO standard. And this way, products can be handled anywhere in the world. Ships, trucks, and wagons are all designed to work with this standard size of containers. And this versatility is a tremendous value. With software containers, it's very much the same. One of the popular definitions says a container is a standard unit of software that packages up code and all its dependencies, so the application runs quickly and reliably from one computing environment to another. So we have this aspect of versatility and portability at the first place. And containers solve important problems. They enable developers to package up an application with all the parts it needs to run, such as libraries and other dependencies, and ship it out as one image that can be executed in any environment that support containers runtime. And from the historical point of view, containers were initially introduced for web applications and microservices development. Ability to isolate the dependencies of multiple application components and scale up or down depending on the load on the application was a huge benefit for the IT world's enterprise server applications. Now we see containers being used in basically all areas of software development, including embedded and safety critical space where C and C++ languages are dominating. With the growing complexity of embedded systems like AI-based autonomous driving, teams are looking for solutions to manage and maintain more and more complicated toolchains. And even though containers were initially developed for a slightly different purpose, they fit this picture very well. They allow to effectively manage complex development environments. And currently there are many companies involved in providing container-related technology. We have multiple commercial and free of charge options available. And the best known name in the industry, which is often used as a synonym of container technology, is Docker. And in the diagram on the right-hand side, you can see an example architecture of a Docker-based system. You can see containerized application in the top layer. They are placed on the Docker container engine layer. And as the diagram shows, containers are isolated execution environments. They have their own processes, own network interfaces, and mounts. Just like virtual machines, except that they share the same OS kernel. And for some of you, it may be interesting, how are containers different from virtual machines? So let's take a quick look, how do they compare? This diagram shows the comparison of containers and virtual machines. On the right, you see Docker engine based system stack. At the very bottom, we have the underlying hardware, then we have operating system, and then Docker is installed on the top of OS. And Docker engine manages the containers which run our applications packaged up with all libraries and dependencies. On the left, we have a system stack that is based on virtual machines. Here again, at the very bottom, we have the hardware layer that runs the hypervisor, which manages the virtual machines. And as you can see, each virtual machine includes its own copy of OS. Then we have dependencies, libraries, and finally the application. And these multiple copies of operating system, which is the case for VMs-based setup, cause higher consumption of underlying resources. Each operating system will need processing power and will steal some CPU cycles. The same is with the disk space. With every VM, we need to have a full copy of the operating system, which is usually counted in gigabytes and takes significant time to boot. With containers, the situation is different. Containers need less CPU as they share the same kernel. We also need less disk space as containers need to carry only application-specific software, which can be only several megabytes. And finally, containers are much faster to initialize as they utilize the running kernel. So as you can see, containers offer a lot of advantages, and in most cases, they are the answer to the problem. There are few cases, however, where virtual machines may be a better choice. For example, if your application needs to run on a non-Linux operating system, such as QNX, or when security is absolutely critical for you. In such case, virtual machines offer better isolation and protection of your critical assets. Now, let's take a look at a couple of key concepts and terms. First, let's differentiate between container and container image. The container is the actual instantiation of the container image. And there is an analogy here to object-oriented programming. A container image is like a class, and the container is an instance of the class. A Docker image basically packs up the application and environment required by the application to run, and a container is a running instance of the image. Now, how do you create container images? Well, images can be created with Docker files. And Docker file is a recipe for container image. In the Docker file, we can find instructions that build the image. When instructions are executed, Docker creates layers that compose the image. And layers can be shared across multiple images. To some degree, layers resemble the inheritance in the object-oriented programming language. Right, so another important concept is tags or are tags. The same Docker image might have multiple different versions identified by their tags. And tags provide a great support for versioning and traceability. A good analogy here is how Git, for example, Git tags refer to particular commits in the history. And finally, last but not least, sharing images. Container image, once built, can be shared via registries. And a Docker registry is a storage and distribution system for named Docker images. The registry allows Docker users to pull images locally, as well as push new images to the registry, assuming, of course, adequate access permission. And by default, the Docker engine interacts with Docker Hub, which is Docker's public registry. There are also other public registries available online. And if needed, it's also possible to run on-premise Docker registries. There are free and commercial options available here. And finally, just to close the introduction part, I would like to share a few words about the orchestration. Container orchestration is the automatic process of managing or scheduling the work for individual containers. Container orchestration is all about managing the life cycles of containers, especially in dynamic and large environments. So it is an automated process and can be used for many tasks, such as provisioning and deploying containers, redundancy and availability of containers, and also scaling containers up and down to distribute application load evenly across our hardware infrastructure. And also many other tasks. It's a really broad subject. The most popular tools for container orchestrations are Kubernetes and Docker Swarm. You probably have heard these names. And when you use a container orchestration tool, you typically describe the configuration of your application in YAML or JSON files, depending on the orchestration tool. And these configurations files are where you tell the orchestration tool where to pull container images from, how to establish networking between containers, how to mount storage volumes, and where to store logs for containers. And typically, teams will branch and version control these configuration files so they have consistent behavior of containerized applications. And this is probably all I wanted to cover regarding the introduction to containers.
Well, that was very educational, and it really laid out a solid foundation for understanding where we can build from. Miroslav, can you now tell us how containers are used and configured for use in an embedded C and C++ ecosystem?
Yes, actually, this is a very interesting subject. In general, in the last few years, we see a trend among the organizations developing embedded and safety critical software to modernize the tool chains. Many teams are switching to agile and adopt modern approach to software development. And containers are a very important part of this transformation. They are becoming more and more popular, especially in the automotive industry. And containers are used in so many ways that it would be difficult to cover this subject entirely in the frames of the webinar. So as it was already said, today we will be focusing on the selected aspect of using containers for development toolchains deployment. And here are a couple of points why embedded development teams, especially the large ones, love containers. And the first thing is the centralized management. Tools like compilers, SDKs, or static analyzers need to be deployed in a consistent way to the entire team. Any kind of discrepancy in the toolchain becomes a significant problem when you work in a big team. And containers are really great here. Image with the compiler or SDK can be created by, say, for example, infrastructure team and automatically deployed to all team members with just one click. Another aspect is the ability to dynamically react to changes. For example, when a security vulnerability is detected in one of the libraries, containers allow us to quickly patch it and do not worry that there is a machine somewhere that was not patched and we are risking the faulty build. And another thing that is very important for the teams developing safety critical software in the regulated environments like with ISO 26262 is the ability to version the development environment and keep track of all the updates. When already certified product requires maintenance, team needs to use the exact version of the toolchain that was formally approved for this product at the certification time. With containers, it's very easy to revert the toolchain back to any version from the past. So this is a really great advantage. And last but not least, with containers, the cost of onboarding the new team member is significantly lower, especially for the teams that use complex toolchains. With containers, the new team member is ready to work in a matter of minutes. So let's see now some of the typical scenarios. I've mentioned that in the last few years, we see a transformation in the industry and adoption of modern development methodologies and toolchains. And a very popular combination of tools we see now includes like Linux development hosts, Git for source code management, GNU GCC compiler, CMake, lightweight code editors like VS Code or CLion, Jenkins for the CI automation, and of course, Docker. And these tools can be deployed in many different ways. And in the next few slides, I'm going to show you a couple of simplified examples how containers can be introduced to the development environments. Here we see the setup without containers. In this scenario, all the tools that are required to develop the software are installed directly on the development host. This has many significant disadvantages, which we sort of already discussed when talking about advantages. Maintaining this kind of development environment, especially for a large group of developers, is very difficult. How to synchronize the updates of compilers, etc. So the first step that we can make to apply containers in our development is to containerize the runtime environment for the application. The development tools like compiler, linker, build system can be still installed locally, but the execution environment is deployed in the container. This assures sterile conditions for running the application, identical as in production environment. And this is a great step towards eliminating it works for me syndrome that frequently happens when developing and testing complex products. With a runtime environment in the container, whenever there is a change, the execution environment can be updated in one place and consistently roll out to all developers in basically very short time. And it works equally well even in the cross-platform development environments. So containers can be combined with emulators like QEMU, and they provide reliable test execution environment, for example, for ARM-based platforms. And this is something that highly simplifies the testing process and enables easy automation and brings a lot of savings in the testing process. And actually, we have many customers using this type of configuration, as I said, especially for ARM-based systems. In the next step, in addition to the runtime environment, we can use containers to deploy the development toolchain. So compiler, linker, SDK, all that is needed to prepare the application binaries is deployed in a container together with the execution environment. And one thing to note here, in this diagram that is displayed now, you see that code editor, in my example, Visual Studio Code, outside of the container, and this is the blue icon. It doesn't mean that GUI-based tools cannot be deployed with containers. Even though the primary use of containers is for GUI-less and server applications, there are various ways to enable user interface applications with containers, for example, with VNC. But this is something that requires additional configuration, and it's not always practical. So here in our simple examples, we will focus on the canonical use of Docker containers, which assumes using it for background applications. Hence, the code editor or IDE on the diagrams is still installed on the host. And the next logical step that many teams make when applying containers is to split execution environment and runtime environment into two containers: execution environment and container with build toolchains. Splitting the development toolchain execution environment reduces the problems with managing dependencies. And also it makes the images smaller and easier to update in case of changes. And this is also the configuration we frequently see among our customers. Runtime execution environment is kept as a separate container, and development tools like compilers and build tools are deployed in another container or containers, depending on the complexity of a specific environment. And once our setup with containers is stable, the transition to Jenkins or another CI/CD automation tool is very easy. And here again, Jenkins is shown as installed directly on the host machine, but Jenkins can be also deployed in the container. And finally, a very important subject: sharing container images with the development toolchains across the team. Without effective sharing mechanism, we would not be able to take advantage from all the benefits that containers offer. And there are many ways to share containers. Again, detailed discussion of all the options is far beyond the scope of this webinar. But one of the options is to share the Docker file via the source control and allow the team members to build images locally. But most likely, we will want to share container images via the registries. And if there are no legal or business obstacles, we can share our images via the public registries like Docker Hub and make it available for everyone. And if we need to limit the access to images and enable them for our organization only, we can set up a local registry available only within the boundaries of our organization. So with registries filled with container images, our team has one place to go to get an update. And this gives us all the benefits we have discussed and allow our organization to easily scale and reduce the toolchain maintenance burden. We have central management of the toolchains. We have ability to dynamically apply changes and react to security vulnerabilities, ability to version the toolchain, and lower onboarding cost for the new team members.
Wow, there are so many benefits to using containers, like each team member getting a consistent development environment to work from, and version upgrades being so easy to do. Plus, having that flexibility that you mentioned to revert the development environment to specific states, it's just crazy wonderful. I can now also see the productivity and how onboarding costs of bringing in new team members is lowered. And the immediate security benefits that containers bring about are also so important, especially in today's world. I also found the various scenarios and configurations you presented were very informative. And I'm sure that it's given a lot of ideas to our viewers right now on how they may want to configure their deployment of containers within their organization. Now, Miroslav, can you let our audience know and show us how they can deploy containerization using Parasoft C, C++ test with Docker containers?
Sure. Thanks, Ricardo. So what I'm going to discuss now is not any different from the scenarios we have just covered in the previous section. I would like to give you a little more details regarding the usage of Parasoft tools in the containerized development environments. I'm going to present this with our flagship product, Parasoft C++ test, as an example. And for those of you who are not familiar with our offering, just quickly a few sentences about C++ test. C++ test is a unified testing tool for C and C++ code testing. Its unique value is support for multiple source code testing techniques, which is very important for achieving compliance with safety standards like ISO 26262, DO178, BC, IEC 61508, and IEC 62304. It supports static code analysis and can be used for achieving compliance with the standards I just mentioned, but also with the coding standards such as MISRA, AUTOSAR, or CERT. It offers feature-rich unit testing framework with code coverage, stubbing, and ability to execute test cases on the host, target, and simulator. And all functionalities are supported with compliance reporting framework and certified by TÜV Süd, which simplifies the process of tool qualification and approving for use when developing safety critical software. And Parasoft C++ test is available as a plugin to Eclipse, Visual Studio, and Visual Studio Code. And it also supports the pure command line mode, which enables using it in the fully automated runs in the CI/CD pipelines. So we will discuss how to use C++ tests with containers in the two workflows that are typically used by our customers. First workflow is with C++ tests at the developer's desktop, where tools is used as a plugin to the IDE. And the second workflow is based on the command line, where the tool is used, for example, at the CI/CD pipelines. And this diagram presents the IDE-based workflow. In this scenario, we assume that IDE and C++ tests are installed on the development host. Here you can see I have an Eclipse icon, and below we have the icon that represents C++ tests, this rectangle with pluses. and compiler toolchain as well as the execution environment in this scenario are provided in containers. And this is the setup we see to be very popular among our existing customers, as I mentioned a couple of times, especially in the automotive space. And during the regular build, IDE invokes the in-container build process where compiler and linker are executed to prepare the final binary. And typically this process is managed via some kind of build scripts, and the IDE does not interact with compiler or linker directly. The build process is isolated from the host environment and happens entirely in the container. When configuring C++ test to work in such environment, users needs to remember about the following things. The container with the compiler toolchain needs to be running in the background so that C++ test can execute the compiler whenever needed without the overhead of starting the container for every invocation. C++ test, second thing, C++ test build settings need to be adjusted to invoke compiler and linker in container. By default, C++ test is using compiler linker executables, and this has to be changed. In 2020.1 release, we've introduced a special wrappers for compiler and linker that enable usage of in-container compilation toolchain and highly simplify the configuration process. All that user needs to do is to configure the name of the container that should be used by setting the appropriate environment variable. And the last thing, the source code and the temporary files generated by compiler and linker need to be visible for C++ tests on the development host. And one way and the most effective way to assure this is by volume mapping the Eclipse workspace. And that's basically it that is required to prepare C++ tests to work with containerized toolchains. I will be showing it in a few minutes during the demonstration part. And as I've mentioned, in 2020.1 release, we have enhanced the internal process that is used to run the code analysis, specifically around the unit testing. So the configuration for Dockerized environment is now really simple. Now, let's take a look at the second workflow. Here we see the configuration that is typically used for command line runs at the CI/CD pipelines. Build tools, compiler toolchain, and execution environment are deployed in container. In this scenario, Jenkins triggers the process, which goes through the build of the source code and the testing process, which may include static code analysis and unit testing with Parasoft C++ test. When configuring C++ test to work in such environment, user needs to do one main thing. That is, prepare the container image, which includes the compilation toolchain, build tools, and C++ test. And the process of building the container image is done with a dedicated Docker file and shall include the installation of C++ test inside the image, as well as configuring the license settings via the special property files that are also added to the image to use appropriate license server. Currently, we recommend using network licenses for network floating licenses for Dockerized setups. And the C++ test standard edition version 2020.1 includes an exemplary Docker file, which can be used as a base to create the final Docker image. And once the container image is ready, it can be made available via the registry and automation frameworks can invoke the code testing tasks in the container. And that's basically it. I will be showing it again during the demonstration part. So now let's see a quick live demonstration to illustrate our discussion so far. I'm going to show you how you can use C++ test with containers in the two workflows we have just discussed. So let me close the slide deck and switch to my virtual machine. So first, we will start with the command line based workflow example. Let me bring up the slide just for a moment to visualize what we are about to see. Our goal here is to enable our team with a container image that includes C++ test, so that it can be deployed to automation servers for execution in the CI/CD pipelines or to developers' desktops for local command line runs. So what we want to do is to build a Docker image with compiler and C++ test inside. So let's see how we can do it. What I have here is the C++ test distribution. This is something you would get when downloading C++ test from the customer portal. I'm going to start by unpacking it. It will take just a second. And as I mentioned in our 2020.1 release, together with C++ test distribution, we are shipping the dedicated Docker file, and you can find it in integrations Docker directory inside the C++ test installation. Let's take a quick look. So this Docker file shows all the important steps that are required to build the image with C++ test. Of course, in the real development environment, you will need to customize, modify this Docker file, possibly merge it with your current Docker file. But nonetheless, it's a good base for doing it because, again, it shows all the important steps. So what I'm going to do now is I'm going to copy this file to my local folder. And also, I'm going to copy one additional file. This is a property file which contains the details of my license server. I'm going to include this file in my Docker image because I want C++ test to be automatically configured for using the license server from my environment. We can take just a quick look. It's just a couple of settings for configuring the license. So what we need to do is we need to uncomment the line in the Docker file, which will copy this property file to the installation location of C++ test in the container. So let's save the changes and quit. And now we are ready to build our image. Let's name it C++ test CLI and give it a tag latest. And we're ready to build the image. It will take a moment, but I've built this image previously on this machine a couple of times, so most of the time-consuming steps are already cached, so it should be no longer than 20 seconds. That's it, and we have it. Our image with compiler and C++ test is ready, and And we can test it using a command line, exemplary command line that is attached, that is added to the exemplary Docker file. So what I'm doing right now is I'm copying this command line that is commented in this file. I'm going to paste it here. I will slightly modify this command line and I will add one more option to generate the report. And we are good to go. With this command, I'm going to run the static analysis on the exemplary project called ATM that is stored in examples directory inside the C++ installation. And the analysis will be done with the default set of static analysis checkers. So let's run it. As you can see, container is started, and inside the container, static analysis is executed. C++ test got the license from the license server. I specified in the property file, and now analysis is in progress. And now we're done. As you can see, 4 static analysis violations were found. Here we see them on the console. That's an output from the process running in container. And we can also quickly see the report that was generated afterwards. So we see all the findings here. We can drill down in the report and we can see specific problems found here. So this concludes the demonstration for the command line based development workflow. What we have just seen was how to create a container image using the exemplary Docker file that is shipped with C++ test, and how to run static analysis in the container. So now let's see a quick example of the IDE-based workflow. And let me bring up a slide again to visualize what we are about to see. So our goal here is to configure the C++ test that is a plugin to Eclipse in this demonstration to first use the in-container compiler toolchain to build unit tests and also possibly perform the static analysis. And second, configure it to use containerized runtime environment to execute unit tests. So what I have here is the C++ Test Professional Edition. This is again the version 2020.1 with a demonstration workspace. And I'm going to show you what are the steps required to prepare C++ tests to use the containerized toolchains. And the first step we need to do is change the build settings, C++ test build settings, and replace the compiler executables that are used in the typical host-based setups for the analysis with a special wrapping scripts that are shipped together with C++ test. You can find it in integration/docker directory. And these wrapping scripts are designed to execute the compilation and linker in containers. So that's the first step. I have already done it here. Second step is to tell these wrapping scripts what is the name of the container that should be used for the compilation, for invoking the compiler. And We decided to do it with help of environment variable that is called CPP test container name. Here you can see I have exemplary script that I'm using to start C++ test IDE. And in this script, I'm setting the variable to custom GCC, which represents my container where I want to run the compilation. And this approach with environmental variable is very flexible because it's easy to apply, for example, with Jenkins, and then it's very easy to switch from one container to another. All we need to do is just to modify the value of this environmental variable. And these wrapping scripts I was showing to you a second ago, they will basically use another container. And the third thing we need to do is to actually run the container in the approach we are using for the integration with containerized toolchain. We assume that the container with compiler and linker is running in the background, and C++ test is only executing the command lines in these containers. It's for performance reasons. It's just much faster to execute, invoke these command lines in a running container instead of starting the container for every process. And it can be done in many ways. It can be done with scripts. In this setup, I have two launch configurations created for it that start and stop my container. And we can quickly check. We can quickly check, and we see that the container which holds my my compiler is running and ready to use. So now we can quickly generate unit test cases. Test cases are successfully generated. We can see them here. Just a couple of examples. And now we are ready to execute generated unit tests. And to do so, I will use built-in test configuration that is shipped with C++ test. Its name is run unit test in container. And it will basically build the test binary using containerized compiler. And then once the test binary is ready, it will be executed in container. So the process runs now. It should take no longer than 10 seconds. We are linking, and unit tests were executed. The console now shows the results. We see some tests are passing, some tests are failing. We can see results in a quality view, some runtime problems from automatically generated test cases, typical situation. And also if we double click on the code, we see that that we have code coverage. We have these highlights here represented cover lines. So our tests were successfully executed using the containerized runtime environment. And you can see here this wrapping script was also used for running the tests. In this specific example, I was using the same container for compilation and for running the tests, but it can be easily configured to use different container for building, for compilation, and different container for running. And that's basically it. As you can see, with the enhancements we are providing in 2020.1 release, you can easily configure C++ tests to work in containerized toolchains. And with this setup, swapping compiler to and execution environment is trivial and can be done in minutes, if not seconds. And even I already discussed it, but even if I work in the regulated environment and in 5 years from now, I will have to revert my toolchain to the version used in the past to fix the bug in the old release, I can still do it in minutes, and my effort to do it is very low. And this concludes the quick demonstration. Let me go back to my slide deck for a short summary. So just to summarize, in the last few years, containers became an important part of the embedded development process. Teams use containers in many different ways and for many purposes, but they value containers especially for managing and developing complex tool chains and development environments. So scalability, maintainability, isolation, and security, these are all very important aspects. And Parasoft tools fully support containerized deployments in both lines of our products. Our tools for testing at APIs level have been deployed in containerized environment for many years. In the last few years, we also see a great interest from our customers to use source code testing tools, especially C++ tests and C++ tests in containerized environment. And we expect that the growing complexity of embedded development environments will result in increased usage of containers. And with this being said, we have reached to the end of the presentation. So Ricardo, back to you.
Okay. Thank you, Mirek. That was very impressive. You made it look so easy, and I really learned a lot watching that. It actually removed a lot of the mystery about containers for me. You know, and then I also learned about the workflows that you show and what to consider, and that they also play various roles in the phases within the software development, like early on in the code implementation phase where developers can perform static analysis and find defects early from the very get-go, you know, where it's easiest to fix all those defects and least expensive. Then you show those unit testing and having all of this incorporated into your continuous integration, continuous delivery, you know, that can be done within the containers. And I love that it shows it's efficient, modern, and an evolutionary approach to development of embedded applications. So Miroslav, thank you very much for sharing that knowledge with us. And I think now it's a good time to open things up for questions. Let me see here. I see that we have several questions. So here we have a question. Do you plan to make the container images available via the public registries like Docker Hub?
That is a very interesting question, and the answer is not at this point. We had a couple of requests for it, but most of our clients are wanting to build images themselves and have a full control. They have complex development environments, complex tool chains, and it's important for them to have a full control over the process of build image. But if we see more requests, we will consider it. All right, I see some more questions coming. Next question, how do you handle licensing in the containerized environments? Well, again, this is a very good question. And containerized development environments are by nature very dynamic. So currently we recommend using network floating license. And okay, we have some more questions. There is only Linux host. How does Docker integrate into Windows host, Windows toolchains? Well, with Docker containers are supported on Windows, but actually what it is that you're running a virtual machine that emulates Linux, that runs Linux, and then you run containers in this machine. So it's really like doing it on Linux. And currently, we officially support using our tool chains with containerized tool chains only for the Linux platform. But if the containers will get more mature for the Windows platform, we'll also consider supporting it. I see another question. Do you have integration for Visual Studio Code as well, or other IDEs? Well, the main integration targets for C++ tests are Visual Studio and Eclipse. However, we just added a plugin, an extension to Visual Studio Code that allows to run and work with static analysis, and we'll be adding more functionalities. And we are also looking to add integration into other editors like CLion. Do you also consider, next question, do you also consider to use Docker to run unit tests on target? That's something that is fully possible right now. If you have your cross compiler in the container, you can easily configure C++ tests to use this cross compiler exactly in the way I just showed. And with this, you will get the binary that is built for your specific target, and then you can execute it on the target. If your target supports containers, you can also easily configure it that way. I guess in this situation, we are talking about Linux-based target system. And what is the next question? What is the hardware requirement for running CPP tests inside container? Okay, here we do not add any other special additional requirements on the top of a Docker engine. So if your system is able to run Docker, then you should be also fine with C++ test. When you want to build the image, which includes C++ tests inside, as in the example where I was presenting this command line based workflow, you need to have a space in the image for C++ test distribution, and this is at least several hundreds megabytes. But if you are working in a limited environment and size of the image really matters, then you can easily customize the distribution, eliminate the parts components that are not needed. If you are facing this challenge, I recommend talking to our support team. They will give you instructions which pieces of the distribution can be chopped off from the image based on your specific use case. And I think these are all the questions. Mm-hmm. So I believe we are ready to close the session. That's just about time. Passing back to you, Ricardo. Mm.
Okay. Yes, that's all the time we have. Thank you, Miroslav, for a wonderful presentation and answering the audience's questions. Today's webinar has been recorded and will be made available later today along with the slide presentation. So expect to receive links to this collateral. Please also look out for an email about Parasoft's upcoming webinars. We have several, so please don't miss out on those. And don't forget to visit our website, parasoft.com. You will find additional information on this topic and other solutions that we offer. Now, better yet, evaluate our products for yourself. You can also contact us via email, info@parasoft.com, and you can find us on LinkedIn, Facebook, and Twitter. Please follow us. Stay safe and healthy, and thank you again for attending. Bye-bye, folks.